You know that incredibly frustrating feeling when you're in a heated argument, you lose, and then 10 minutes later, usually when you're in the shower or driving home, the perfect comeback hits you.
The French call that l'esprit de l'escalier, staircase huit. The realization of what you should have done, but only after the event has passed.
Exactly. The hindsight is 20/20. Now imagine if you could take that moment of clarity, travel back in time 5 minutes, and update your brain so that you actually said the perfect thing in the moment. And more importantly, imagine you could update your neural pathways so you never miss that beat again.
That is a surprisingly accurate, if slightly metaphysical metaphor for the paper we are covering today.
Welcome back to the deep dive. Today, we are unpacking a paper that I think solves one of the most persistent headaches in machine learning, the credit assignment bottleneck. We're looking at reinforcement learning via self-distillation, or SDPO. This is coming out of Zurich, Max Planck, MIT, and Stanford.
It's a heavy-hitter collaboration, and for good reason. They are tackling the fundamental inefficiency of how we teach large language models to code or reason.
Right. And to understand why this paper matters, we have to look at the status quo. Most of the industry right now is obsessed with RLVR reinforcement learning with verifiable rewards. We see this with models attempting math problems or writing code.
It's the standard paradigm. You give the model a problem, it generates a solution. You run the code or check the answer. Did it work? Yes or no?
With binary.
It is effectively a scalar reward, 1 or 0. And while that sounds logical, think about the signal loss there. Let's say a model writes a complex Python script. It's 50 lines long. The logic is perfect, the architecture is sound, but on line 48, it forgets to handle a 0 division error. The code crashes.
In standard RLVR, that's just a fail.
Correct. The model gets a 0. It doesn't know that the first 47 lines were brilliant.
Nothing.
It just knows I failed. It's like a teacher handing back an essay with a big red F at the top and 0 marginal notes. The student has no idea why they failed, just that they did.
And that creates the bottleneck. You have to run millions of samples just to get enough lucky passes to reinforce the right behaviors. It's incredibly inefficient.
Precisely. And this is where the paper pivots. They argue we are leaving massive amounts of signal on the table. They are proposing a shift to RLRF reinforcement learning with rich feedback.
Rich feedback being the compiler screaming at you.
Essentially, yes. When code crashes, it doesn't fail silently. It gives you a traceback. It says index error, list index out of range on line 12, or timeout error. That is a dense, token-rich signal. The problem has always been, how do you mathematically feed a text error message into a gradient update?
Right, because a policy gradient algorithm like PPO or the newer GRPO group relative policy optimization expects a numerical score, not a sentence. You can't just plug syntax error into the loss function.
That is the gap SDPO bridges. The method is called Self-Distillation Policy Optimization. And the core mechanism is fascinating because it eliminates the need for an external, smarter teacher. The model teaches itself.
So let's get under the hood here. How does it convert syntax error into a math update?
It utilizes the model's own capability for retrospection. Let's stick with our coding example. The model, let's call it the student, tries to solve a problem. It generates an attempt, Y, it fails. The environment returns the feedback, F.
The traceback.
Right. Now, in a standard loop, you just throw that away or maybe try again. But SDPO takes that feedback F and the original question X, and it reprompts the same model.
It effectively asks, given that you made this specific error, what should you have written?
Exactly. This creates what they call the self-teacher distribution, denoted as theta of something given X and F. Because the model now has the error in its context window, the benefit of hindsight, it is significantly better at predicting the correct tokens than it was the first time around.
I see. So the model isn't smarter in terms of parameters, but it's smarter in terms of context.
Yes. The presence of the error message collapses the probability space toward the correct answer. It looks at line 48 and says, oh, clearly I shouldn't divide by 0 here, and assigns a high probability to the fix.
So now you have two distributions. You have the original dumb attempt where it crashed, and this new hindsight distribution where it knows better.
And that allows you to calculate a dense supervision signal. They use a distillation loss. Specifically, they minimize the KL divergence between the student's original distribution and this new self-teacher distribution.
Let's unpack the KL divergence aspect for a second.
Yeah.
We're measuring the distance between how the model did act and how it should have acted.
Correct. But here is why this is revolutionary compared to GRPO. In GRPO, you get a reward for the whole sequence. It pushes the probability of every token up or down uniformly based on the outcome. But with SDPO, because you are comparing logits token by token against the teacher, the signal is granular.
So the self-teacher can agree with the student on the first 47 lines, saying, yes, keep these high probability, but specifically diverge on line 48.
Precisely. It provides token-level credit assignment. It effectively says, your logic for the loop was fine, don't change that, but this variable assignment, that was wrong.
That solves the sparsity problem. You're getting a gradient update at every single step of the generation.
And the math reflects that. The gradient looks very similar to a standard policy gradient, but the advantage term, which usually comes from a reward model, is replaced by the log ratio of the teacher's probability to the student's probability.
Now, looking at the objective function in the paper, they mention a stop gradient on the teacher term. Why is that necessary? If the teacher is just the model reprompted, shouldn't we update both?
That's a crucial stability detail. Remember, the teacher is just the model itself with extra context. If you allowed the gradients to flow through the teacher, you'd be trying to move the teacher toward the student at the same time you're moving the student toward the teacher.
They just meet in the middle.
They would collapse into a middle ground that might not be optimal. It's a moving target problem. Exactly. You need the teacher to be the anchor. You say, this hindsight distribution is the truth. Freeze it. Now move the base weights to match this. Without the stop gradient, training becomes unstable.
Speaking of stability, they also mentioned using an exponential moving average, or EMA, for the teacher weights. This reminds me of techniques used in things like BYL or other self-supervised learning setups.
It's the same principle. Instead of the teacher being an exact copy of the current, erratic student weights, the teacher is a smooth, averaged version of the model's history. It dampens the noise. It ensures that the target distribution doesn't jump around wildly just because of one weird batch update.
Okay, so the mechanism is sound, but does it actually work? They tested this on LiveCodeBench v6, which is notorious for being a difficult, contamination-free benchmark.
It is. The results were stark. They compared SDPO against a highly optimized version of GRPO. On the pass rate accuracy, SDPO hit 48.8% compared to GRPO's 41.2%.
In the world of coding LLMs, a nearly 8% jump is significant.
It's a generational leap in performance without changing the underlying model architecture. But the metric that really matters for anyone training these models is sample efficiency. SDPO achieved GRPO's final accuracy in 4 times fewer generations.
4 times faster.
Because the signal is dense, the model learns from every failure immediately, rather than waiting for a lucky success to reinforce a behavior.
There was another result in the paper that I found almost counterintuitive, especially given the current hype cycle. It's about verbosity.
Ah, yes, the length of the response.
Right. We've all seen the new reasoning models. They generate these massive chains of thought. Let me think about this. Wait, I need to check. Let's recalculate. We've started to equate the length of the output with the quality of the reasoning.
We have. And algorithms like GRPO often accidentally encourage this. If the model finds that generating a long circular chain of reasoning gives it more compute time to stumble on the answer, the RL will reinforce that verbosity. It's effectively reward hacking. It's stalling for time.
Exactly. But SDPO showed the exact opposite behavior. On chemistry tasks, the SDPO models generated responses that are up to 7 times shorter than the GRPO baseline, yet they had higher accuracy.
7 times shorter. That is a massive reduction in inference cost.
It's huge. The authors suggest this happens because the credit assignment is so precise. The model doesn't need to engage in superficial reasoning or circular logic to find the path. The self-teacher points directly to the logic gap, so the model learns the direct route.
That implies that effective reasoning doesn't have to be verbose reasoning.
It implies that a lot of what we currently see as reasoning traces might just be computational bloat caused by inefficient reinforcement learning signals.
That is a fascinating takeaway. But I want to play devil's advocate on the self-teacher concept. This whole system relies on the model being able to look at an error and fix it. What if the model isn't smart enough to do that? That is the hard constraint. The method relies entirely on in-context learning, ICL. The model must be capable of understanding the error message. The authors found that SDPO performance scales directly with model size.
So it worked on Qwen 3.8b.
Yes, significant gains there. But when they tried it on Qwen 2.5 1.5b, not so much.
The gains evaporated.
Or regressed. This suggests that the ability to self-teach from feedback is an emergent property. If the model is too small, showing it a complex traceback doesn't help. The teacher distribution is just as confused as the student distribution.
You can't distill knowledge that isn't there.
Exactly. You need a certain baseline of intelligence for the hindsight to be valuable.
I want to shift gears to the section of the paper that felt the most like a glimpse into the future. They discuss something called test time self-distillation. This addresses the very hard tasks.
This is where we challenge the limits of what inference means. The authors looked at tasks where the base model has a success rate of near zero. Pass at 64 is less than 0.03.
So standard RL fails here because you're exploring a pitch black room. You never find a solution, so you never get a reward, so you never learn.
Precisely. Zero gradients. But with SDPO, even a failure is useful because it generates an error message. The innovation here is that they perform test time training.
Walk us through that. The model is deployed. I ask it a question. It fails. What happens?
It fails. It gets the runtime error. Instead of just trying again with the error in the prompt history, which is what we do now with multi-term prompting, SDPO actually performs a gradient update on the model's weights, right there on the fly.
It updates its own parameters based on the error.
Yes, they describe it as compressing context into weights.
That's a powerful concept. Usually if I have a long conversation with a model to debug code, eventually I run out of context window. The model forgets the beginning.
Right. But if you are updating the weights, you are baking that learning into the model itself. The context window stays clear, but the model has learned the lesson.
And the results on these unsolvable tasks.
Impressive. SDPO accelerated the discovery of solutions by 3 times compared to best-of-K sampling. On tasks where the baseline was stuck around 35–40% success rates, the test time SDPO approach hit 53.2%.
So it essentially debugs its own policy until it solves the problem.
It turns the test phase into a training phase. It blurs the line completely.
But isn't that computationally expensive? Running back prop at inference time.
It is expensive compared to a single forward pass. But remember the verbosity point. If the model can solve the problem in 3 iterations of weight updates versus generating 30 pages of circular chain of thought reasoning, the weight update might actually be cheaper in terms of total FLOPs.
That's a fair trade-off. Now, for the engineers listening who might want to implement this, there's a practical bottleneck here. Computing KL divergence requires storing the full logit distribution.
And with modern vocabularies of 100,000 plus tokens, storing 2 full sets of logits for every token in a batch is a VRAM killer.
So how do they get around that?
They use top K distillation. They realize that for any given token, only the top, say, 100 choices actually matter. The probability of our aardvark appearing in the middle of a Java function is effectively 0.
So they just truncate the distribution.
They take the COP-K logits to calculate the precise divergence, and they sum the rest into a tail bucket. It approximates the full KL divergence with negligible error, but saves massive amounts of memory.
Clever engineering.
Yeah.
I also want to touch on the ablation studies, where they disable parts of the system to see what breaks. We know rich feedback is key, but what constitutes good feedback?
They compared a few sources. Obviously, the environment output, the runtime error, is the cornerstone. But they found that if you also have access to a gold standard solution, maybe from a separate successful rollout, combining the error with the correct solution works best.
Makes sense.
Yeah.
Here is why you failed, plus here is what success looks like.
But there is a negative result that is really important for prompt engineering the self-teacher. They tried including the student's original failed attempt in the teacher's context.
You mean showing the teacher, here's the code you wrote that crashed, and here is the error.
Yes, and that actually hurt performance.
Why? That seems like useful context.
It biases the teacher. If the teacher sees the student's original code, it tends to anchor on it. It produces a distribution that is too similar to the error. It reduces exploration.
So the teacher's effectively saying, well, I wrote this, so it can't be that wrong. Let me just tweak it.
Exactly. Whereas if you just give the teacher the question and the error, it forces it to reconstruct the solution from scratch, often leading to a radically different and correct path.
That is a subtle but crucial distinction. It's the difference between editing and rewriting.
Perfectly put.
So summarizing the contribution here, SDPO allows us to use any tool that provides textual feedback compilers, linters, LLM judges as a dense training signal. It removes the need for a super teacher like GPT-4, and it produces models that are more accurate and less verbose.
It effectively turns the entire software ecosystem into a training data set. We don't need human annotators to label every step. We just need code that compiles. It transforms any LLM into a process reward model, a PRM, through retrospection.
Which bridges the gap between the exploration of RL and the supervision of distillation.
And it does so efficiently. We aren't just getting better models, we are getting models that reason more efficiently.
I want to close on the implication of test-time self-distillation. If this method proves scalable, we are looking at a scenario where models are never truly frozen.
That seems to be the direction.
Right now, we think of a model as a static artifact. I download the weights, I run them. But if SDPO works, the model could be constantly debugging its own weights based on the specific errors it encounters while solving my specific problems.
It implies that the weights become fluid. A model solving a physics problem might temporarily fine-tune itself into a physics specialist via one-time errors, solving problems that the base model technically shouldn't be able to solve.
It creates a bespoke intelligence for the duration of the task. It really challenges the definition of what it means for a model to know something. Does it know the answer, or does it know how to learn the answer?
In the end, with SDPO, those might be the same thing.
A fascinating shift in perspective. That's it for this deep dive into reinforcement learning via self-distillation. Thanks for listening, and we'll catch you on the next one.